Okay, my goal now is to put it all together here with a new example. This is the example that is in that document that you have too. So now you have the document notes, you have the video to see how it all kind of unfold live, and I hope you can put all the pieces together now and get this whole eigenvalue first strategy. So first of all, here's how it starts. System of linear differential equations. We know that if straight line solutions exist, if eigensolutions exist, we know that those dx dt's are going to boil down to a lambda times x, and we know that dy dt is going to boil down to a lambda times y. So we saw that over here, and there's good reason for that too. Maybe we'll talk about in class. So dx dt is lambda times x, dy dt is lambda times y. Now, we can go through the rigmarole, or we can just get to the good stuff. And the good stuff is this. We know that we're going to end up with a 2 by 2 determinant. And that 2 by 2 determinant is going to be 4 minus lambda. Let me make that look better. And I hope you can see why. If you subtracted lambda x from both sides, you're going to have that 4 minus lambda because of the like terms here. And then we're going to have a 1. And then we're going to have a 2. And then we're going to have a 3 minus lambda. And I hope you can see where the 3 minus lambda comes from. If we subtracted lambda y from both sides and combined like terms, we'd get 3 minus lambda. Now, some of the theory on this thing, I know is a little difficult to wrap your brain around, but this determinant has to come out to be 0 in this dependent system that we're leveraging so that we can get all the solutions. And so this determinant has to be 0. To evaluate a 2 by 2 matrix like this, we multiply minus we multiply. That's how you do it. So we're going to take 4 minus lambda, multiply it by 3 minus lambda. Minus 1 times 2 is 2. This thing has to be 0. Let's clean up, do some algebra here. Let's see, it's going to be 12. Minus 4 lambda minus 3 lambda. Do you see the outers and inners? Are going to give you minus 7 lambda. Plus lambda squared minus 2 is equal to 0. Clean it up a little bit. We've got lambda squared. We've got minus 7 lambda. And we've got plus 10 is equal to 0. And you're welcome. Once again, we're going to see a nice factorable situation. Hey, if the quadratic doesn't factor nice, though, you've always got the quadratic formula. Or you've got technology just to play along with this method here. But at some point, some way, get the real solutions. Now, if we don't have real solutions, then I'm going to ask you to just not solve. And we'll just look at some phase planes and kind of wrap it up with that. But for now, we're going to focus on solutions that are real eigenvalues. And so this one, factors. We're going to have a lambda and a lambda. We're going to have a minus 5 and a minus 2. Check that out. Lambda squared minus 5 minus 2 is going to be the minus 7, and then minus times minus is a plus 10. Yep. So eigenvalue 1, 5. Eigenvalue 2, 2. So like we saw in our example previous, we do have two nice whole number, real number eigenvalues. Hey, if it's not nicely factorable and you have a quadratic formula, you can have eigenvalues of like 2 plus the square root of 7 all over 3 or something. It's just the way it is, deal with it. But focusing on real results here, not imaginary results, we're going to continue by writing our solution. So our solution would look something like this. In matrix form, we're going to have x of t, we're going to have y of t. And x of t is going to equal a constant, I'll just use C1, and then it's going to be e to the, let's go with the 5t first. And then y of t is going to be, we'll call it C2, e to the 2t. But then we're going to need an associated eigenvector and an associated eigenvector. Now the eigenvectors come from the eigensolutions, the straight line solutions. But remember, in this method, we found the eigenvalues first. Then we'll find the straight line solutions. In the previous case, we found the straight line solutions first, and then found everything from there. So we just now need to get our straight line solution. So it goes like this. Suppose we consider lambda equals 5. if lambda equals 5, then we can come back here. It doesn't matter which. In fact, I'll show you that it doesn't matter which. And we can now say that 4x plus 2y is equal to lambda x. Therefore, let's subtract 4x from both sides. Let's divide both sides by 2. So the associated eigensolution, straight line solution, is y equals 1/2 x. And so we can do something like when x is 1, y would be 1/2. If you don't like having a fraction in there, you could make it nicer and say, well, when x is 2, y is 1. Do you see? You have some freedom there to choose your solution. We'll talk about the rest of that later, but just to show you that we could also have done this, x plus 3y is equal to lambda y, 5y in this case. Let's subtract 3y. That would give me a 2y over here, divide by 2. So you see it wouldn't matter, we're going to get the same straight line solution. But then, what about when lambda equals 2? In the case where lambda equals 2, then we would have 4x plus 2y equals lambda times x. Let's solve for y. Subtract 4x, that would be negative 2x, and divide by 2, y equals negative x. So we just want to make an associated eigenvector to connect with that eigensolution so that we know that it comes from y equals negative x. So simply 1 and negative 1 would work. So there's your solution. I was going to say something else about it. I lost it. I hope it all comes together though now in terms of the method, the process, how we got some of these pieces from the document, and you can now see the solution. Oh, I could have done this just to make sure you're good. It doesn't matter which line you pick. X plus 3y equals lambda y in the case of lambda equals 2. And so if you subtract, and so yeah, y equals negative x. So that is the case. All right, there it is.